Okay, I think we can start now. So we just want to look at the last method for solving nonlinear systems of equations. And then we will see if we can also start another chapter. But I'm thinking maybe we can just finish this last method. And then on Friday, we start looking at another chapter. Okay, so let's talk about Newton's method now. Newton's method. So like I told you on Friday, we are just going to look at two methods for solving nonlinear systems. So on Friday, we looked at the fixed point method, and we saw how it can be used to solve nonlinear systems. So now let's talk about the Newton's method. So you looked at the Newton's method, the time we are solving equations involving one variable, and you used to call it the Newton-Raphson method. You used to call it Newton-Raphson method. And you said if you have a system of, if you have an equation and you want to find a zero of that, and then you can approximate that value using this formula. So it will be more like the fixed point method, but only that the function g is given in this way. So it will be the same as xk minus 1, then minus f of xk minus 1 divided by the derivative evaluated at k minus 1. Okay, and then you'll be given, of course, the starting point x naught. So you'll be able to substitute in there and be able to find the zero. So we'll try to do the same. Now, in this case, of course, we are solving a system of n equations in n unknowns. Maybe we can represent it in this way. We talked about this system on Friday. So we just try to see how we'll be able to use the Newton's method. Okay, so I have n equations, fi, all of them are equated to 0. So we'll try to see how we can generalize the Newton-Raphson method, and then this will give us the Newton's method. Okay, so when we are using the Newton's method to solve nonlinear systems, then we'll be able to generate a sequence xk, where xk will be given by capital G k minus 1, which will be equal to, now in this case, we are going to have xk minus 1, then minus the Jacobian matrix evaluated at k minus 1. Then we find the inverse of this. Then times f of xk minus 1. I've run out of space here, but I'm sure you're able to see that the last expression there is just talking about capital F evaluated at k minus 1. And of course, we know that this G, so maybe let me write what those matrices mean or what they are. So in this case, we know that G X is just this matrix containing this column vector, so to speak, which will contain these functions G1 up to Gn. Okay. And then this Fx, like we said, will just contain these functions, which we are calling F1, F2, and so on up to Fn transpose. And then this J, Jx is the Jacobian matrix. This is a Jacobian matrix. And it is given as follows. So let me write it on the next board. So Jx will just be given by partial derivatives of f1r with respect to x1, then partial derivative of f1 with respect to x2, and so on up to partial derivative of f1 with respect to xn. And then I'll continue doing this, and then I'll also find partial derivative of fn with respect to x1, and this should continue. And here I'm going to have a partial derivative of fn with respect to xn. So I'll come up with that matrix. Okay. So once I find this matrix, then I can be able to substitute in that formula to generate a sequence xk from k equal to 0 up to infinity, right? So this is the method we are going to use. Of course, here, what is important is just to look at this function, capital F. We'll get this function from the individual functions that we have been given in the system. So I'll get F1, and then using this, I can find fx to power k minus 1. Okay, so I need to use the initial value or the initial approximate, which will always be given. You'll be given those values, and then you should be able to find this. Now, you'll notice that every time you are evaluating xk, you need to find the inverse of this Jacobian matrix. Okay, so if you don't want to find the inverse of that matrix, then you can use this other way of evaluating xk. Okay, so how are we going to do it? We are going to let the whole of this be equal to yk minus 1. Okay, if the whole of that is equal to yk minus 1, then I can multiply the Jacobian matrix to the left-hand side. Remember, in this case, I have those matrices, right? They are matrices, so I can multiply the Jacobian matrix to the left-hand side on both sides of that equation, and then I'll be able to express xk in terms of xk minus 1 and yk minus 1, okay? So if you want, you can use those two methods to solve the same system. So what do I mean by that? Like I've said, xk in this case is given by xk minus 1, then minus the Jacobian evaluated at xk minus 1, inverse, then times f over xk minus 1, right? So what we are saying is we let the whole of this be equal to yk minus 1, okay? So what we are saying is, I'll stop writing x in there. I will just know that this J inverse means the Jacobian matrix evaluated at xk minus 1. So that expression means J inverse F is equal to y. Okay, so like we said, I can now multiply the Jacobian matrix to the left-hand side. So what will that mean? So it will mean, of course, I have a negative. Let me write the negative here and this y somewhere here so that I can have enough space to write the Jacobian matrix. So I can multiply the Jacobian matrix there and the Jacobian matrix there to the left-hand side of this equation, so that I just get minus f is equal to jy. Okay, so if I don't want to find the inverse of this Jacobian matrix, then I can use this equation. Okay, so from this equation, I'll be able to get a system of linear equations. Okay, so if you want to avoid finding the inverse of the Jacobian matrix, then just know that you will get to the system of linear equations. So these linear equations will be in terms of yi, okay, where each yi is a component of this capital Y. And then after finding that y, I'll be able to substitute in there. So that from this equation, I'll be able to get xk will be equal to xk minus 1, then plus yk minus 1. So that's what I'll be able to get. Let me write this nicely. So what I'm saying here is when we do that, we should be able to get now the equation xk is just equal to xk minus 1, then plus yk minus 1. That's what we'll be able to get. So after finding this y from this system of linear equations, I can just substitute in there to get xk. Okay, so you can do this, or you can just find the inverse of that Jacobian matrix. If you're comfortable with finding the inverse of the Jacobian matrix, then you'll be able to do that. But just know that for each k, you have to calculate that Jacobian matrix and its inverse in order for you to find the solution. If you don't want to do that, you want to use this y, then just know that you have to solve that linear system of equations for each k, and then you'll be able to find the approximate value. Okay, so that's what we are going to do in this last method. And then we'll use the same example, example 3.2.1, to apply this Newton's method. And of course, when you check in the notes, I've left out certain steps. I know that you can easily verify the values that we have in there. You can easily follow the other steps that I've left out. It's very easy to do that. Okay, so let's go to that example now. So we are using example 3.2.1. If you can remember very well, we're given this system of equations, 3x1 minus cos x2 x3 minus 1 over 2 is equal to 0. Okay, and then we had x1 squared minus 81, x2 minus 0.1 squared. No, it's plus here, not minus. Okay, then plus sine x3 plus 1.06 is equal to 0. And the other equation was e to power minus x1, x2, then plus 20 x3 plus 10 pi minus 3 over 3 is equal to 0. Okay, so we have this system, and then the initial approximation x naught is just equal to 0.1, 0.1, negative 0.1 transpose. So like I mentioned in the other lecture, this initial approximation will always be given. You'll be given this, and then you can find other approximate values. Okay, so from these equations, I can find my F1. So remember, we said Fi will be equated to 0. Okay, so I can see that all these equations are equated to 0. So it means F1 in this case will just be this 3x1 minus cos x2 x3 minus 1 over 2. Then F2 will just be this equation, x1 squared minus 81 times x2 plus 0.1 squared plus sine x3 plus 1.06. And lastly, F3 will be given by e to power minus x1, x2 plus 20 x3 plus 10 pi minus 3 over 3. Okay, so that would be my last equation. So in this case, I don't need to make xi the subject of the formula for each I. I just need to take my function the way it is, and then I can find the Jacobian matrix. So I'll find the Jacobian matrix in terms of x1, x2, x3. And then I'll be able to evaluate this Jacobian matrix and F, capital F, at the given initial point or initial approximation. So if F1, F2, F3 is equal to that, then I can write my capital F, capital Fx in this way. F1, F2, F3 transpose. Okay, so I'll be able to substitute the values that I'll be given. Okay, so first of all, let's find the